So the research that Nicolò and I are doing starts from this very simple fact that when you ask how mathematicians make mathematical discoveries, you cannot ignore the role of analogy and analogical reasoning. Okay, so the role of analogy has been discussed extensively in the in the literature on science, the philosophical and psychological literature on scientific reasoning. We are trying to point out and underline also the role of this analogical form of reasoning in the context of pure mathematics. Okay, and in order to do that, we want to start with a quote from Simone, from the correspondence between André Weil and Simone Weil. Right. As you know, André Weil is a very famous mathematician. Simone was a very famous philosopher, and there is an interesting part of their correspondence, which in Italy is published as a little book, which talks about the process of mathematical discovery. Roughly, Simone asks André, the brother, exactly how his work kind of develops, and the answer from André Weil is interesting. I actually recommend this book highly because André is going to say that in fact analogy plays a very prominent role in the process of his developing mathematics. So when Simone asks, so what exactly are you researching on? André responds, Arting functions in the abelian case are polynomials, which one can express by saying that these fields furnish a simplified model of what happens in number fields. Here, there is thus room to conjecture that the non-abelian Arting functions are still polynomials. This is just what occupies me at the moment. Okay, so this is an example of an analogical extension of a property in one known familiar domain into a different another domain. And he goes on then to praise the role of analogy in a mathematical discovery. He says, nothing is actually more fecund than these slightly adulterous relationships, by which he means relations of analogy between distinct mathematical domains, and nothing gives greater pleasure to the connoisseur. Now, when thinking about analogical reasoning in mathematics, we have approached this issue from the perspective of epistemology. From this perspective, the main questions are first to describe the implicit norms of good of strong analogical reasoning in mathematics. That is to say, an account of what makes a particular piece of analogical reasoning a better or a weaker example of that reasoning, right? Or what makes a conclusion derived from analogy more or less plausible. Okay, so that's the one important question. And there is another question, which is what justifies, in practice, the use of analogical reasoning in a domain such as mathematics? That is to say, assuming that there is such a thing as an important distinction between weak and strong analogical argument or analogical inferences in mathematics, exactly how do we justify their use, the use of these analogical inferences in the discipline of mathematics? Okay, so on these topics, Nicolò and I have developed two current papers which have been recently published. One, Reasoning by Analogy in Mathematical Practice, which was published recently in Philosophia Mathematica, and another one which was just published a few days ago in Erkenntnis, has to do with giving an account of what in the philosophical language we call confirmation from analogical inference or from analogy. Now, our aim today is actually not so much to discuss the details of these papers, which I, of course, hope you will read, but to actually branch out. So we'll try to do something more brave. We'll try to talk about how the philosophical approach that we've defended in the previous paper, in these papers, bears on two main issues. Well, the first issue is the relation of epistemology, the epistemological theory that we spelled out, with psychology. Okay. And the other issue that we want to talk about is the relation of this epistemological theory with pedagogical practice. Okay. Now, I should do a big disclaimer here, which is that neither Nicolò or I are either psychologists or experts in mathematics education. Okay, so all that we're gonna do is to try to bring out a series of related points established by means of proper philosophical methodology, the methodology that is distinctive of the philosophical sciences, in order to question, if you like, in order to raise questions better about the foundational elements of psychological theory and pedagogical practice. Okay. It should be clear in advance that so far, at least, we haven't performed any form of experiment. We don't have any kind of empirical evidence, right, on the subject. Although we believe that the approach, looking at this looking at the subject from the perspective of the philosophical, the epistemological approach that we developed, has the potential to raise interesting and important empirical questions. Okay. So in particular, I'm going to talk about the relation of epistemology with psychology, and then I'll sort of leave the ball to Nicolò to describe a very small set of exercises that we developed in the last few months in occasion of the International Day for Mathematics here in our department. Okay, so you'll see kind of the beginning of an application of our approach in pedagogy, but that requires further development. Okay, so in order to spell out the basic idea behind our approach, our epistemological approach, we want to start discussing a few examples. The examples will be very simple and will concern more or less the same issue. That is to say, the fact that in mathematical practice, there is a big perceived difference in how analogical inferences are assessed. Okay, so there are clear, I think, phenomenological differences between stronger and weaker analogies in practice, in the process of mathematical discovery. An example of this has to do with the Euler characteristic. Okay, as you know, in the 2D case, in convex polygons, the number of vertices and edges is exactly the same. We can express this relation by saying that V, the vertices, and E, the edges, are equal. The number of vertices and edges is the same. Now, historically, Euler asked if any similar regularity holds for in the 3D case for convex polyhedra. Now, the correct answer, as it turns out, is that the three-dimensional case is governed by the relation that you see as 2 on the slides. V minus E plus F equals 2, where F is the number of faces of the polyhedron in question. Okay. Now, what we're going to consider is 2 distinct analogical inferences one might have performed in order to arrive at the correct conclusion. Okay, so we're imagining a situation, as it were, in which we don't know if the Euler characteristic holds because we don't have a proof of it, and we're imagining a situation in which we are therefore trying to come up with a kind of a heuristic that will lead us to the right answer or to the proof. Okay, now Polya suggests an argument of the following kind. It's a very famous book on induction in mathematics. He says, look, you could rewrite 1, that is V equals E, as 1 star, V minus E plus F equals 1. And by noting that there is a kind of alternating sum of the essential, the main geometrical elements of the in the 2D case, there is a V minus E plus F and so on. You could have inferred by analogy that an algebraically similar alternating sum relation holds in the 3D case. Okay, so the main property that we are extending here is this alternating sum. Now, it turns out that historically, this is not how the Euler characteristic was actually achieved. In fact, historically, Cauchy reached the right conclusion, namely the Euler characteristic, by means of a kind of geometrical reasoning. So the basic idea is that we think of a polyhedron, like say a cube, and we think of it as smashed or flattened. Okay, so we think of this polyhedron, we think of smashing it or flattening it. After that, we link some of the old edges of the polyhedron by these little dotted lines that you see on the top figure in the slides. And we start and with that, we obtain a bunch of roughly triangular surfaces. Okay, so of course, the edges of this figure may not be, the same anymore. They could get curved and elongated in the process. But what matters is we get roughly triangular surfaces. Okay, as the shaded surface that you see, the gray shaded surfaces that you see in the figure. Now, what happens now is that you think that you consider the fact that any removal of a roughly triangular surface would leave a figure that has exactly the same number of vertices and edges. Okay, so, or at least that the relation between vertices and edges in the figure remains constant. And this applies both in a case like we're removing we're removing a triangular surface of the top kind, and we're removing a triangular face of the latter kind, of the bottom kind. Okay, in all cases, removing triangular surfaces would leaves the relation between vertices and edges roughly invariant. Okay, now our point is, of course, this sort of reasoning in here involves, in a sense, analogical reasoning. It involves an analogy, let's say, between the flattened polyhedra and polyhedra in the 3D case, okay? But we think there is an important difference in strength between the two arguments that we've just provided. Um, the former, the Polya-inspired algebraic reasoning, seems to us to be based on a rather accidental algebraic similarity between 1 star and 2, namely the alternating sum similarity. On the contrary, we think the geometrical reasoning that Cauchy exhibited is stronger in comparison. In fact, historically, Cauchy regarded his argument as a proof of the Euler characteristic. In fact, we think it's best to see it as a kind of a strong analogical argument, because for reasons that we won't get into here, the Cauchy's argument doesn't actually amount to a proof. Okay. Now, how does this difference in strength bear on psychology in particular? Well, a lot of psychology on analogical reasoning has as its object the dynamical process of analogical reasoning. So it emphasizes what they call the heuristic function of analogy in the mathematical domain, namely the capacity of analogy to raise questions, to provide the means of exploration in the mathematical domain. But what we're pointing out here is that this idea of the heuristic function is, I think, too rough. It insufficiently captures what an analogy can mean for the working mathematician. That is, no doubt, analogy has a heuristic function. It could result in a schema abstraction, as many people in psychology call it. That is, they could abstract away from the specific circumstance into something more general. It could shift in certain ways our perception of a given target. This is in psychology also called re-representation. But we think there is an important also difference at the phenomenological level between deeper and more superficial analogies in mathematical research. Okay, and in fact, a few of the mathematicians who have reflected on discovery in mathematics have, I think, pointed out something similar as what we're discussing. For instance, Hadamard, in this famous book on mathematical discovery, writes that mathematical training consists partly in developing a discriminating faculty, which consists in the capacity to differentiate between what he calls mere hookings, suggestions, hints, the basis for a kind of exploration in the mathematical domain, and what he calls relay results, more telling results, more telling, in the case of analogy, more telling similarities. Okay. Now you might think, well, this difference between what we're calling hookings and relay results, between weaker and stronger analogical inferences, or more superficial and deeper analogies in mathematics, may be accounted for by psychology, in particular by the predominant paradigm of in cognitive science about analogical reasoning, which is the so-called structure mapping account of analogical reasoning, defended, among others, by Deirdre Gentner. Okay. In particular, if you recall Gentner's approach, she defends the idea that an analogical inference is stronger, first, if there is a kind of one-to-one correspondence between the terms in the source and the target domain. This is usually how we represent an analogy in psychology and in philosophy. There's a model or source, there is a target. And so the first thing is that we want a one-to-one correspondence between the properties in each domain. Okay, and then Gardner has an additional requirement of what we call structural alignment. Okay, so in a way, we have a bias, as she calls it, for structures, for matches of structures that are in some sense more systematic and explanatory. That is to say, we, in a way, tend to think of an analogy as stronger than another, according to Gardner, on the basis of just how much match in relational structure there is between the relations that the properties of the source entertain between one another, and on the other hand, the relations that the properties of the target entertain with one another. This is, in other words, the requirement that the analogy is, in some sense, systematic. Okay, so whereby analogies that are more systematic are supposed to be better. Okay, analogies that display a larger amount of structural alignment is supposed to be is perceived as a better or a more plausible or a deeper analogy. Okay, that's the Gardner approach, and a lot of which inspires a lot of thinking about analogy in cognitive science. But actually, I think there is an important and open question whether anything like that approach can apply plausibly to pure mathematics. And to show this, I want to show you quickly another simple example. We're using, examples that are easily accessible. Usually it's from 2D to 3D case, but there are many other examples that we could have used instead of actual analogies in mathematical research. Now, in this case, it's a matter of extending a property of the triangles in the 2D case to tetrahedra in the 3D case, right? So we know in the case of triangles that the three middle points of the edges of the triangle, right, intersect in a common point. That's called the barycenter. So that's the red dot that you see on the top right figure on the slides. Now, the question that we want to ask is it then plausible to think that the four medians of a tetrahedron similarly intersect in a point, in a common point, in a single common point? So that will be kind of the barycenter of the tetrahedron. But by median, we mean the point that links the barycenter of each face of the tetrahedron with its opposite vertex. Now, again, there are two ways of getting at this, of doing, let's say, the reasoning for a plausible positive conclusion. One starts off from analytic geometry or the Cartesian scaffolding. Okay, so knowing that the analytic expression of the triangle's medians, x, y, z on the top part of the slides, has a certain form, certain algebraic form. We could infer that the three-dimensional, the 3D equivalent of that of the medians in the 2D case will also have the shape that you see on the bottom part of the slide, the algebraic form that you see for x, y, z, and w in the bottom part of the slide. And by trivial mathematical calculations, you could eventually get to the conclusion that yes, the three medians of the tetrahedron actually intersect in a single point. Now, another way of looking at this, again, doesn't start from the Cartesian scaffolding, but from pure geometry. So we know that the existence of a barycenter in the triangle case, in the 2D case, is guaranteed by so-called Ceva's theorem. Now, from this, and this is very important, and in a way, from implicitly articulating our knowledge of the important similarities between triangles and tetrahedrons that we are perhaps unable to articulate that, but that we have a clear understanding of, right? So it's a kind of a visual or implicit knowledge or understanding of the analogies between these two kinds of geometrical figures. Then we reason that just as the barycenter in the pure geometry case is a kind of center of mass for the triangle figure, right? Speaking improperly, but effectively about the subject. So it's plausible that tetrahedron will also have a similar center of mass. Okay, the reasoning here is, of course, using an improper language, but I think it comes closer to understanding how exactly the mathematical reasoning in this case goes. Okay, from in another case of analogy from 2D to the 3D case. Now, this example is useful because I think it suggests very clearly that structural alignment, as Gentner and other people in the cognitive science literature shows, the structural alignment is insufficient for explaining the difference between weaker and stronger analogical arguments in mathematics. That's because, roughly, we believe that, again, the geometrical reasoning that we looked at later is, we think, stronger than the reasoning that we looked at by the Cartesian scaffolding, which is based on a kind of an algebraic extension of properties known to hold in the 2D case. But notice that in both examples, structural alignment holds. That is to say, it is true both for the algebraic end of the geometrical resemblance, that there is a high degree of structural alignment between roughly the relational structures that the properties in the 2D domain entertain, the relation between those properties and the properties in the 3D domain. In fact, it's even worse because we know that Ceva's theorem holds for the 2D domain in the pure geometry case, but no known analog of Ceva's theorem is known for the 3D case. And so, in a way, you have perhaps more structural alignment in the reasoning from the Cartesian scaffolding than in reasoning from the pure geometry case. However, it's clear that the judgment as to which of these two reasoning is stronger goes strongly in favor of the pure geometrical reasoning. Okay, so we have a plausible case in which the amount of structural alignment would favor the analytic geometry case, but where in fact the analogical inference is stronger in the pure geometry case, despite lesser structural alignment. Okay. Now, so what follows from this? Well, if that's right, roughly, what the consequence of this could be that we need, in some way, to rethink the relation between analogical reasoning as studied in cognitive science and the implicit norms that seem to be apparent from a study of what should we say, the phenomenology of mathematical discovery in practice. Okay, so we should have to conclude that the psychological theory that we've been exposed to, the paradigm that comes from Gentner's and others' approach, is in fact incomplete in some respects, because it doesn't capture the difference in strength between different analogical inferences in the process of mathematical discovery. Now, this is the conclusion that we anticipate, as it were, but of course, we don't have yet any sort of experimental evidence that to sort of play in the same ballpark as Gentner. So we leave this kind of exercise as future work. But I think we've made at least a plausible argument that something is missing in the standard paradigm in the psychological literature on analogy mathematics. Now, why is this important for pedagogy? Well, it's kind of simple. Teaching analogically is thought to be, in mathematics, is thought to be a very important part of mathematics training. It's important for students to develop a notion of how one could, as it were, guess a particular mathematical property or fact from a simplified model. Okay, so given that this is a standard way of doing research in science and also in mathematics, as we discussed, it seems to be an important target for teachers to develop this kind of model-based attitude in students. However, this form of teaching is notoriously difficult. Students, in fact, often fail to recall relevant examples that they have been exposed to. Okay, so, or encode content in a situation-specific manner, so sometimes are unable to generalize in the way that would be required in order to see the analogies between one domain and another. And solid results only seem to be obtainable with highly trained students. Some studies, in fact, estimate at least 10 years of training to possess the relevant skill in understanding and managing analogies between mathematical domains. Now, of course, because people see value in a model-based or an analogical, in developing analogical skills in students or skills in generalization and seeing patterns, connections, there's been a lot of studies trying to accelerate this form of learning. But we think that, again, there's a question about these proposals insofar as they're based on a specific theory, psychological theory, about what analogical inference consists in, right? Or what good analogical reasoning consists in. Of course, if you disagree that structural alignment is what we should look for, then we should also maybe rethink some of the pedagogy and the pedagogical approaches that are inspired by that psychological theory. And again, this is a quote from Polya that I think captures a little bit what we are trying to say. In a way, the idea is, look, when you teach mathematics, you have to teach this difference between cheap and valuable generalizations in mathematics, which is puts in terms of diluting versus condensing. Right? He says there are two kinds of generalization. One is cheap and the other is valuable. It is easier to generalize by diluting a little idea with big terminology. It is much more difficult to prepare a refined and condensed extract from several good ingredients. I think this idea would resonate with a lot of people who either teach or research in mathematics, right? So to how to make students understand this difference between diluting and condensing is what we're looking after. I'm gonna be very quick about this, but roughly speaking, our approach is based on developing an analogy between, if you like, a meta-analogy between the student who learns a particular mathematical domain, a new mathematical domain that is unfamiliar to him or her, and the mathematical researcher in the activity of puzzle solving. The idea, in other words, is to put students in a circumstance that is as close as possible to that of the researcher, the mathematical researcher, who doesn't know what the answer to a particular question, mathematical question, would be. And to try to insert in this context some nudges, some suggestions, some hints of how to use a model based on analogical inference in order to get to the right result, or to the correct answer. We think this approach has the potential to overcome some of the main problems for, and again, speaking as some outsiders from this discipline of mathematics education, for what we think are two approaches to mathematics pedagogy. Right? Representationalism, which in a way analogizes mathematical learning to perception, and constructivism instead, which tends to see the mathematical learning more like a construction rather than as a perception. Okay, those two families of approaches have problems in terms of their practice, because in the case of the representationalist approach, teaching somebody about a particular analogy isn't like perception, right? To display an analogy to somebody who doesn't have the concepts that you have is very difficult. Okay, we had a slide earlier about somebody who tried to teach the primary school kids about the analogies between the words of rods and numbers. And we assume that he says Holt, this is Holt in a paper a long time ago, we assume that children looking at the rods could see how the word of numbers worked, the operation between the rods analogized by the operations of the numbers, and vice versa. But that experiment failed, right? Because the children could not see the analogy that they were assuming would be easily perceived by the students. At the same time, we think that the analogizing student with researcher also can overcome some problems with constructivism, in the sense that it leaves room for leaves bigger room for a productive use of student imagination, right? Rather than trying to be explicit about all the behaviors you wish your student to display, as Brousseau puts it. which runs the risk that, as it writes, they will display this behavior without recourse to the understanding. The approach that we have sort of experimented with in the latest and our latest exercise here in collaboration with Domenico Brunetto and Caterina Bassi in Politecnico di Milano. The approach that we are defending, or that we are suggesting here, puts students in a situation to have and want to use their imagination, so also their modeling skills in resolving mathematical puzzles. Okay, so I'm going to leave the word to Nicolò to briefly illustrate a few of the problems that we used and how they involve analogy and model-based reasoning.
Okay, thank you, Francesco. So now in these last few slides, I will try to explain how the framework introduced by Francesco, based on analogy and analogical argument, can be used to construct a set of exercises that can lead the student to use analogical argument or something similar to produce the correct answer. I want just to point out the premise of these kind of problems. In particular, I want to underline that these kind of problems are part of a bigger context. Indeed, we have organized as Francesco said before, an event for the International Day of Mathematics last March, in which we tried to create a mathematical escape room, namely a mathematical game for high and middle school, in which the students had to solve 6 different problems and 6 different conundrums by using also some hints that we prepared to make a particular way to make a particular way to solve this kind of exercise. So I want to present 3 of these problems, in our opinion, the most interesting for this talk, this lecture. And so I start from the first application, which is about the tetrahedron. Actually, we use pyramids because we create a context, because we talk about an escape room with a particular context. But now I just skip all the framework, all the story created around this event, just to focus on the problem and the method we like to present today. So let us imagine to live in a tetrahedron, and we want to find the path of minimal length which connect the 4 barycenter, the barycenter defined before by Francesco, of the face of tetrahedron, starting from one of them. So the students had the idea of tetrahedron given by a photograph. Actually, was a pyramid, as I said before. But we provide them also the 2D development of the pyramid or the tetrahedron in this case, that they could use or not as they want. But in the case you can see of the two-dimensional version of tetrahedron, you can see that the length, the path, you can just write down the path of minimal length in a more simple way as in the 3-dimensional case. Indeed, as you can see on the right of your display, the 2-dimensional version is actually the same as 3-dimensional version once you have reconstructed in this way. So our hope was actually that students use the hint, the two-dimensional hint we provided them to better understand the way to pass between the 2D case and the 3D case, which is actually the same. So the analogy here is that once you found the answer for the two-dimensional case, you have actually also found the answer for the three-dimensional case just by this kind of reconstruction. It is very similar to the argument explained before by Francesco about Cauchy, the Cauchy argument for Euler characteristic. And so we hope that this kind of problem could lead the students to have a similar way to argument in mathematics. Another interesting problem in such a direction regards the problem of the cube. Let us imagine to have a cube and paint it in a color, for instance, in red. Then you can divide this big cube in 64 identical small cubes. And then we take these cubes, these little cubes, and put like in a sack, and we want to extract one of them, and we ask about the probability to find a little cube with exactly two faces colored in red. So we start with a big cube, we divide it in a small cube, and then we ask for a probability. There are many different little problems here, but again, we provide to the students a two-dimensional version of the cube, again inspired by the Cauchy argument for Euler characteristic. And as one can see, there is the possibility to divide by using, for instance, this development of the cube in two dimensions. Divide the faces of the cube in 64 six small for each faces we can divide by 6 lines, and then color in red. Now the point is that in this particular case there are two different ways to proceed, and there is a big difference between this kind of problem and the previous one, because in this case, okay, it's true that the two-dimensional version is analog for the colored face to the three-dimensional version. Indeed, we can reconstruct the cube in the same way as before, but we need increased attention, because as you can see, in the case of a two-dimensional cube development, we need we needed to identify some edges which are actually the same. So it's a little bit difficult for a student to find this direct link between the two-dimensional case and the three-dimensional case. And however, one can just take this kind of two-dimensional development to reconstruct the 3D version of the cube and just count how many little cubes have exactly two red faces. So there are two ways to work with the two-dimensional version of the cube, which lead to the same conclusion. So we want to emphasize that such a problem is very interesting also to understand the way of thinking about this kind of problems for the students, because yes, you know, we want to use maybe some students use the 2D approach, our 2D hint, maybe not. And so it's very interesting. We are now collecting the answer from the schools involved in this event to understand if they have used or not this kind of analogical argument between 2-dimension and 3-dimension. And finally, as last application, I want to present a completely numerical problem, which in my opinion, also in our opinion of our team here in Politecnico, was maybe the most difficult, yes, because you know, when you talk about geometry, is something you can like think about something concrete. When you talk about numbers, something that you think about something abstract. So I want just to show you this kind of problem. We provide we imagine a world in which every person has 8 fingers, every alien maybe instead of 10. And we provide a table with many numbers as this on the left of your display, and we ask to complete, and in particular to find the question mark on the last line of the table. So the point here is that there are many versions of these problems. We discussed about how to provide a useful version, also to understand if they can take this as an analogical problem between different bases, namely between base 8 and base 10, because you know, when you pass from 10 fingers to 8 fingers, something happened here. But you can just imagine that this kind of table actually hidden the following strategy to solve. So we have in the first column the number, which is in base 8. Then we can use the hint. Maybe it works like the division rule of 9 in base 10, which works in the following way. You take a number, you have to sum all its digits, and then take the remainder of the sum. The remainder of the sum is the when you divide it by 9 in base 10, is the same as the remainder of the original number divided by 9 in base 10. And it turns out that the same argument works for any basis. And the very interesting thing here is the following. You can sum the number in base 10, in base 8, in whatever base you want, and take the remainder on the sum number in the as the division the division by 7 in base 8. So this is very interesting to understand if the students can work on this problem in the same way they work when discovered, in a sense that was explained before by Francesco, of the researcher, when they discovered the rule of division of the remainder division of the division of 9 in base 10. And it's very curious that there are many schools, so many classes that actually can solve the problem. And again, we are collecting the answer of the school to understand how they actually work about this kind of problem, which is actually only a numerical problem. And so to conclude, there are still some open questions which are working now with our team. So me, Francesco, Domenico, and Caterina, we are working together in the same team, FDS of Politecnico di Milano. And in particular, we are interested in to understand what this kind of question. For instance, what sort of psychological features can be derived from variation in student response patterns? For instance, between the two problems involving geometrical argument. The first one I exposed and the second one. And moreover, we can also interested in how can we ensure that the solving methodology for this pedagogical experiment will be most successful, because as Francesco said before, we are like this is new for us, is a new topic, and we try to just understand all the psychological feature we need to make the best work as possible. So I want to conclude, just say that this is a work in progress, and thank you for your attention, and we are open for any suggestion, question, or whatever you want. Thank you very much.